So this chapter looks a little bit more into the nitty-gritty, ultimately, of how stars live their lives, kind of details. In the last chapter, we talked about some important stages of a star's life, like main sequence stage, giant supergiants, white dwarfs, and so we'll be kind of talking about those again in this chapter. But what you're looking at here, actually, is what's left over after a star has gone supernova. So this is a supernova remnant. And as you know from this, the guts of the star like this, we have now heavier elements in that star, in that debris, that supernova remnant, and new stars can be born from that stuff. So most of interstellar space, or most of the space between stars, is a vacuum. There's not much particles of anything, but every once in a while you'll run into these large nebula, and they're small nebula and large nebula, sometimes called giant molecular clouds. These clouds can birth a lot of stars, because we talked about two types of clusters of stars, open clusters and globular clusters, and those sets of stars where clusters are generally born in the same batch of dust, the same nebula. So you're looking at, then, this ends up being kind of like a stellar nursery. Now, on the previous slide, it denoted that when you kind of see these dark areas in this nebula, kind of like we see actually dark regions in the Milky Way, that band of light that goes from horizon to horizon if we have nice dark skies. Those dark regions actually do not mean the absence of dust and that sort of thing. They rather mean that sort of material there is dark, and it's obscuring the light, the star's field behind it. So these clouds are where we can have a lot of stars being born. So as we kind of go through the first part of this material anyway, it sure reminds me of the chapter we talked about the formation of our solar system, and then we talked about the overall how our sun started out as a protosun, and before it was kind of a protosun, it was just kind of a warm blob, and that's how other stars start out. What happens within these clouds is that they are what we call stimulated, and I'm going to kind of show you some pictures of a cloud that has an assortment of little pockets of objects that are going to become stars. But the cloud becomes stimulated, and the first thing that happens is it forms these kind of dense cores, and they're hot. And one of the things that if that dense core ultimately wants to kind of continue to draw in on itself and increase its pressure and temperature in the core so it can have nuclear fusion going on, it needs to, the gravity needs to basically overcome kind of the warmness. The fact that it's warm means that it wants to kind of puff out. So these, sometimes called giant molecular clouds, or GMCs, they contain a few hundred solar masses. And like this second bullet says, is that the objects, the cute little dense cores that want to become stars, they need to cool off in order for gravity to continue to make them contract, so they can heat up just in their core region. So they are kind of oozing thermal radiation, infrared radiation, and radio photons. So let's just kind of look at perhaps the formation of some stars within a common cloud. So here we have this particular cloud is a relatively light cloud. It contains about 50 solar masses. And at some point, I mentioned the stimulation, at some point it gets an outside generally stimulation, makes it kind of become, instead of homogeneous you saw on the previous slide, it becomes a non-uniform. And you kind of see these regions kind of coming together. Those lumpy regions then can be potentially the beginning of the formation of a star. So the lumps then go ahead and they will contract, heat up, and then the heating up will make them want to kind of puff out. So it needs to cool down, and then it can contract some more, cool down, contract some more. So we can get a number of stars formed in the same the pot of gas. So I'm going to go ahead and show you this. I think this is really pretty. There's a nebula. It looks like a nebula from our perspective. Okay, so what your author has done is we can look at it. This is what the region sky looks like in the visible wavelength. I'm going to go ahead and show some labels. So if you, in case you can't read this, this says young stars up here. This says a hole created by stellar wind. And then over here, these two empty circles say protostars. So this is visible. This is in near infrared. And this is in mid-infrared. So finally see mid-infrared, we see those protostars. A protostar is like our proto-sun. It's not yet turned on, but it's an object that is getting some heft to it, and it needs to continue to cool off and contract if it's going to ultimately get the core hot enough and dense enough to sustain nuclear fusion. So let's see, let's go back. That's mid-infrared, near infrared, isn't that cool? And visible. So this is a region in the constellation Orion, and remember the Orion Nebula is the region hanging down from the belt. It's the sword region. And when you look at the nighttime sky, boy, it sure does not look like this, does it? And so what you're looking at is information coming from that part of the sky in the infrared region. And this is, if we're going to go hunting for protostars, that's what we do. So these slides might seem really familiar from the chapter on the formation of our solar system. So remember we said that our sun started out as what we call a solar nebula, which and the solar nebula then got stimulated, and there was a certain amount of rotation to it as well. And so the material contracted into the center. And as it grew smaller, remember because of the conservation of angular momentum, it spun more quickly. And the spinning actually we ended up with this kind of flattened disk that could be our protoplanetary disk, where our beautiful 8 planets formed. Well, kind of adding to that in the formation process, sometimes we would be privy to these jets of material kind of streaming out. This would be from a protostar. The jets of material coming perpendicular, I guess you'd say, to the protoplanetary disk. And here's an example of jets of gas that's coming out of this protostar.